So to continue, in this session, we show you how you can basically model, control, and simulate a mobile platform, a mobile robot on the robotics toolbox. Okay. And what you see here in figure 4.3, you essentially are, this is nothing but the simulation of the equation 4.2, which you saw in the previous section. And here you have, as I said, you have two inputs, velocity and a steering angle gamma. You're going to limit them, because if you don't limit them, then you could damage your vehicle. Okay, and that's already built into your own car. But in this case, you need acceleration limit as well as velocity limit. So this is the cosine of theta. Here is theta. Sine of theta. Then you go and you multiply them by v, and you integrate it. Then you get x, y, and theta. These are your outputs. Okay. There's also a box called handbrake for emergency situations. This is the simulating block for what's called bicycle. Bicycle is a command in your toolbox called bicycle. So this is a way you can model a bicycle in the toolbox. Now we can look at the first application of this in this case. Suppose we want you to model and simulate a vehicle going from one lane and change it to another lane. Okay? Let's say you want to bypass a slow vehicle, you're going to go to the next lane and move on. So here is one lane, here's another lane. Okay. So you have again a steering wheel, you have your speed, you put it into a box. This box is this whole thing right here. This whole thing is incorporated into this box. That's called bicycle. Okay. And you have the simulation result for this, which are shown in this right here. SL_ lane change. This is a built-in, somewhat tutorial command in the toolbox for you to basically understand what's going on. It does not give you the details of how the author did it. However, later on, that's not the case. You'll see the whole thing. This is just for you to go on the toolbox and type in S1_ landscape, and then see the plot. The plot Y is the Y coordinate of the vehicle when it changes from one lane to another lane. It initially goes through a curve, like a convex curve, then it goes to a linear section, then it goes to a concave curve, and it goes there. So it's like going from here, then it goes like this, going there. That's what it is. We go from here and then go that way. So the derivative of y is proportional to theta. So when you have a curvature here, you have a linear ascending value, a ramp, then that linear portion right here is going to give you a constant slope, and then concave one here it's going to have a decaying angle. So this is like x dot, this is minus x dot, this is just x, or t, in this case, just t. So, and then you have derivative of that is going to be your alpha. So this is the simple lane changing vehicle responses as a function of time, motion in the xy location, x and y location. Now let's start using that. Let's start using this capability for some specific missions for the mobile rover. The first one is moving to a point. The idea here is this. You have this could be the floor of your lab, in ACE lab, for example. In fact, that's what is going to happen. You know, our energetic TA will put something on the floor. I think it's already there from Rothschild. On the floor is already something similar to that. And you see, every tile in the lab is going to be one of those boxes. Okay? So, suppose that you have a robot in different poses. This pose is X is 8, Y is 5, and the angle is 90 degrees, right here, this angle. Okay? So this pose, we are going to go to here. This pose, another X, another Y, another angle is going to go here. And so forth and so on. So you have 1, 2, 3, 4, 5, 6, 7, 8. 8 different navigation from 8 different initial pose to a final point. Notice that in this simple first example, we are only specifying the final X, the final Y. We don't care what pose it's going to have. The robot is going to go in that direction at the end and that direction. It doesn't matter. We are not correcting it for the wrong pose. We'll do it later. So here is, for example, an initial. Okay, let me go back. Okay. The distance of the robot at the present time is X and Y. The distance of the robot at the present time to the desired goal, X star and Y star, is the square root of X minus X squared, X star minus X squared plus Y star minus Y squared. This quantity is, if you will, is the correction term, the error of where you are and when you want to be. Okay? As you move along, this error gets smaller and smaller. Okay? So the first control is a proportional controller. Remember, V is one of your control signals. Remember that? Velocity. Velocity is going to be some proportional times the error. Okay? And the second controller, theta, using theta as a sensing value, the angle of the current location of the robot XY compared to the desired location, the angle that it has is going to be tan inverse of the difference of delta Y over delta X. That's by looking at the right triangle. However, there is a theta star and a theta. Theta is your current value, theta star is this one. The difference between those two, this sign is in the nomenclature of your book. If you look at the front of the book, you see 3 pages of nomenclatures of all the terms, vectors, variables, symbols, all are there. So if you see something strange in the middle of your reading, go there. Understand it and come back. So KH, theta star, and this symbol, they call it ang-diff of theta, for positive value of the gain. So this is your second proportional controller. So as you can see, for this simple example, we are going from a given point to the final point for the robot. We are only using two error values, error with respect to the position of the robot, error with respect to the orientation of the robot. We have three variables. Two of them are incorporated here, one of them incorporated here and here. So we have two proportional controllers. If you want to become more sophisticated, you could actually do the same thing using PD controller, doing fuzzy controller, what you may have. Okay. So this turns the steering wheel toward the target. Note that the use of this operator again is the hang diff. Okay, so when you do that, then you just execute S1 underscore derived point and another built-in command in your toolbox, and you do define a goal location 5 and 5, x equal to 5, y equal to 5, and this of course is the Simulink of derived point. Again, your goal is the key. Notice that I don't have any theta here because I don't care where I end up, which direction. I have x, y location. I compute a square root of some of the square differences. I get the error. Multiply by the gain of the P controller, 0.5, I get V. And then here I have arctangent of U2 and over U1, which is right here. This gives me the value of theta star and differentiate the difference with the theta itself, which is a self-feedback line here. Multiply by the gain of the second proportional controller, 4, and I get gamma. And I feed it into bicycle. And bicycle will give me x, y, and theta. And I can record them like here. Okay? So, this section that you see here is designed for the reader to get a generic view of what the toolbox has done for you. If you have any model, you can type that model in your toolbox. You can then say sim, oops. Okay, you can simulate sim parenthesis quote unquote model. It could be derived point, derived lane change, etc., etc. And then over there you will get actually, you can put it all into a variable R, object R, displaying R lists the variable that it contains, and the value is obtained using the find method. So you can, for example, say T equal to R dot find T out. That's a built-in command, and then from there you can actually print Y, print theta, print this kind of value. Okay. Now to go back to that problem, you have your initial pose 8, 5, and pi over 2, which is this 8, 5, and pi over 2, which is this angle 90 degrees. Okay. And then simulate the motion. R equal to sim quote unquote model, in this case S1 underscore derived point. Okay. The variable R is an object that contains again the simulated result from which we extract the configuration as a function of time. For example, configuration Q is obtained by R.find quote unquote Y out. You want to plot it, plot X versus Y, you have plot Q colon comma 1 comma Q colon comma 2, that gives you this plot. Okay. And you keep changing the initial pose, you get all 8 of them by holding the plot. Any questions? Okay. I have to find a way to wake up some of the students in the class, maybe perfume or something. Okay, to wake them up. Okay. All right, now, another potential application here is that you make the robot move from a line, on a line. Force it to go through a line, like, for example, you are, let's say, you're taking driving license exam, and the examiner wants you to drive straight, and there are a bunch of orange cones on both sides. You're not supposed to hit them, okay? So you drive through a line. You follow a line. Let me show you the result, then we come back how we got it. Here's the result. You have different poses, in this case 4 of them, and you want to join this line right here. So you can go like this, one possibility, another possibility, another one, and so forth. So this is a second application of a mobile, navigating a mobile robot. So if you go to equation I.1, where is that equation? That equation is in Appendix I. Appendix I. And here is, let me go to Appendix I. Appendix I are the homogeneous coordinates. It tells you how a point is defined in an n-dimensional Euclidean space. And one of the issues that they covered here, the distance from a point P tilde to a line is given by this equation. So this is the equation of going from a point, distance between this point and a line. Okay. That's where this equation comes from. Okay. So we are dealing with a line curve defined by ax plus by plus c equal to 0. This is the equation of a line in two-dimensional space. A, B, C are given to you, are known. Okay. This requires 2 controllers to adjust the steering. One controller steers the robot to minimize the robot normal distance from the line, which according to equation I1 is given by this. So the distance from a point, location of the current position of the robot, to vertically, normally to the line is given by this equation. The proportional controller is going to be equal to alpha d is minus kd times d. So this is a proportional controller to minimize the distance between the robot and the line. When you reach there and join the line, that d becomes what? 0. Okay, it becomes 0. This turns the robot toward the line. The second controller adjusts the heading angle or orientation, theta, of the vehicle to be parallel to the line. So you want to go minimize your distance and then join in a parallel fashion. Essentially, superimpose it and follow that line. So the theta star is tan inverse of minus A over B. Again, just like previous example, theta star with minus theta has the second proportional controller. Okay. You can combine both of those controllers, KD minus KDD plus KH times theta star for all practical purposes, minus theta, turns the steering wheel so as to drive the robot toward the line and move along it. Okay. So this is the Simulink model for that. That equation you came from equation I-1 is represented in this plot. You put in the value of the distance, Kern distance, and then gives you, and with respect to, it gives you the equation of the line, it gives you the current position of the robot, and gives you the distance, the vertical distance from center of gravity of the robot to the line. If the robot is moving this way, center of gravity is here, and a normal line like that. You multiply by the gain of the controller is here, and you also have a second controller, but we combine them together eventually, and then that's going to have a theta star from here minus theta times the gain 1. So you add those two together or subtract it just like here, and then you plug it into here for gamma. The velocity here is assumed to be constant. In this example, essentially the opposite of the previous example. Remember the previous example, we wanted to move it to a specific XY location, regardless of the orientation at the end. This is just the opposite. Assume constant velocity, but keep working on the orientation to line it up with the line. Okay, that's it. So to do that, you again say derived line, another command. You then look at the values of the line, 1, minus 2, and 4. This is A, B, C, which is this value, 2, and the B and C here. And the initial pose, 8, 5, and pi over 2, remember that? The initial pose was located at 8 and 5 with the angle of 90 degrees with respect to the x-axis. Then you simulate it, call it R. Simulate as 1 underscore derived line. And then you plot it, x versus y, you get this, for 4 different initial poses. Okay? So as you are hopefully begin soon reading this chapter, what I recommend to you to do is to put your laptop next to your book. Okay? You may have issues going electronically back and forth, but if you have 2 laptops, put them next to each other. On one of them you have the textbook, on the other one you have your toolbar. So go through those and then verify, get some practice on the toolbox on it. Okay. Or if you go on the campus, you go to a computer park, you can use one of the university computers and your own laptop. Because your laptop has the toolbox, the computer university doesn't have it. Okay, so that's the second example. Suppose we want to control the robot to follow a path. Once again, here is the actual result. Here's your robot starting from this initial position, 0 and 0, and some angle, a small angle here. You want it to go around and join this circular path. Go around and around. Okay? And hopefully we may try to do this for an experiment in the lab. So your robot will actually start from one corner and go around and around. Okay? We try to do that. before I give it to you, we'll try to do it ourselves in the lab. Okay? Get all the kinks out. So here is what we have. This okay. This problem is very similar to control that we used previously for moving to a point. Instead of moving to a point, we're moving to a path. Okay? Moving to a point from a control point of view is what we used to say regulation. Remember that? Regulation and control. And moving to a path is tracking. That's the second control problem. So, and you remember that in control class, when you want to move to a point by regulating the output with respect to the input, you could use a proportional or proportional plus derivative control. When you want to track your output to go through a particular path, like putting a satellite in an orbit, okay, or a robot moving to a circular orbit, circular path, you need the integral component of the controller. So the control that we used to have only proportional is going to be more than that. It's going to have proportional plus integral at the minimum. So I is the component in the PID or PI control which helps for tracking errors. Okay. The tracking error is equal to this right here. The robot maintains a distance d star behind the pursuit point, and we formulate it as this. So d star is the distance that we know from the known initial condition and the known path. We know from here to here what distance is d star. And any given in between is going to have that kind of error. This is error between where you are and where you want to be. Okay. That we regulate to zero by controlling robot's velocity using a proportional integral PI controller like this. Okay. That's a PI controller. The integral term is required to provide a finite velocity demand when the following error is zero. The second controller steers the robot toward target, which is at the relative angle. Just like before, the desired angle is going to have to be tan inverse of y star minus y, theta is x star minus x. And the second controller can be a simple proportional controller. Is kh theta star minus theta. This turns the steering wheel so as to drive the robot toward the target. Here again, you have another command called S1 underscore pursuit. You sim it or simulate it like this, and you get the variable. Okay. So, and let me see where. Okay, here we go. So, this is now the circle, which is your input, the known path. Its character values are going to be plugged into here. You compute the distance, and you put it on x star minus xy, x star minus x, the square root of some of the squares of x and y. So here you get the difference between where you are and where you want to be. And then I think there's an error here. It should be PI controller. It says PID. Okay? PID may be overkill for this case. Okay? But it should work also. And then this is a proportional controller for the steering part of it. You bring both of them together into the bicycle model, and then you get x, y, and theta as output. If you plot x versus y, you get this kind of curve, which you will have in your homework number 3. You will have 4 problems. One is going to be taking you to Puma 560, the 6 degree of freedom robot you do on the toolbox. You can do forward and inverse kinematics on the Puma 560. And you can do trajectory planning and control all at the same time. And we can plot in 3D box on the toolbox, show the robot moving, all 6 joints of it. And the second problem and third problem will be 2 mobile robot type of this kind of lecture. And the fourth one is the quadcopter. You'll simulate a quadcopter on the toolbox and actually see the quadcopter move in a 3D box in the toolbox. Okay? And that's more difficult of all. Okay, so this is, I'm going to start the third part of the lecture in a minute.